Good morning, ladies and gentlemen. This is Mr. Hunter, and this is your review video for electricity and circuits. The last quiz was on electrostatics, which had to do with just charges, kind of what they do by themselves, which is protons and electrons. And we did like the electrostatic force and electric field. In the previous one, we also worked on electric work and power. So this is going to cover kind of what's left. So uh, from your reference table, we have a few things. So we have voltage equals work divided by charge. And so voltage is kind of how much work you need to do to move a certain amount of charge. Now remember, voltage is called potential difference, and that's your ability to push the electrons. Because remember, in order for electrons to flow, you need a potential difference, which a potential difference is a positive charge on one side and a negative charge on the other, which is what a battery is. So electrons flow, as we know, electrons flow from negative to positive, really, but the convention is backwards because Benjamin Franklin made it backwards and we kept it that way out of respect. So voltage is the ability to do work on a charge. So for example, think about it. If I have a negative charge, right? And then I have a negative charge and I want to push it closer, I have to do work on this charge to actually get it to move closer to the other charge, and that's called voltage. Um, let's see. So then we also deal with, so voltage is potential difference and it's your ability to push electrons. And the unit is volts, because voltage volts. Just like I noted before, you guys really need to learn the vocabulary and you have to learn the units for said vocabulary. I'll actually give you a vocabulary quiz and review for your actual regions so that you can recognize what the units for each term is, because especially on your actual test for this, I saw kids put current as voltage. I saw kids put resistance as current, and it just, to be honest, just really kind of dumb mistakes, but it's because you're not like learning the vocabulary. So you got to put in the work, so pun intended. You got to put in the work so you can actually be successful. So voltage equals uh, volts is that's the unit. And so we have current, which we use the symbol I, and current is going to equal your rate of change of your charge. So current is, remember, the actual flow of charge. It's how fast the charge is flowing, and it's measured in amps. So the unit is amps, or A. So that's the unit. And so it's really a rate of change of charge, which, remember, charge is in coulombs, over time, which is in seconds. So current is coulombs per second, which is also equal to amps. So then we have the last thing, which is resistance. And if voltage is your ability to push electrons, current is how fast the electrons are flowing, resistance is your ability to slow it down or stop it. To stop or slow down the electrons. And the unit for resistance is the ohm. So we use R for resistance, and then ohm is the unit resistance. That's the Greek letter omega. So then because of that, we have, when we have two equations for resistance, one in Ohm's law that relates voltage, current, and resistance, and we have just the natural resistance in a wire. And the natural resistance in a wire is just rho, which is resistivity. It's the P with a squiggly. That's resistivity. It's the natural resistance of a wire times your length, how long the wire is, divided by area. And that makes sense because think about it. If you make your tunnel bigger, more things can get through it. So if I increase my area, I decrease my resistance. They're inversely proportional because, like I said, if I widened like the door to the classroom, more kids could get through at a time. If I increase the length, I increase the resistance because the electrons have to go through more material. And if I increase the resistivity, I increase the resistance because electrons are going to have harder time getting through that type of material. So once again, resistance is rho L over A. Rho is ohms times meter. Length is meter, and then area is meter squared. So the meters all cancel, and you're just left with ohms. And lastly, in terms of voltage, current, and resistance, we have Ohm's law. So Ohm's law is V equals IR. Or if you solve this for R like your reference table does, you just divide out the I, and R equals V over I. You can also do the same thing for I. You could solve it for I, so I would just equal V over R. All I'm doing is solving Ohm's law for the variable that we need. And this also tells you the relationship between voltage, current, and resistance. Like, for example, if my voltage stays the same, if my current goes up, resistance has to go down because you want to keep it match with the voltage. It's just a proportion. And the same token, if my resistance goes up and my current stays the same, my voltage is also going to have to go up to keep the equation balanced. If you're still not clear what I'm talking about, you need to basically just plug in numbers. Like if voltage is 10, if current goes up to, like, let's say current's at 1. If voltage is 10 and current goes up to 20, then resistance is going to have half in order to keep voltage 10. So it's just a simple numbers manipulation. So for the sake of time and because this is review, I need to move on. So now we have the type of circuits. Remember, electricity is the flow of charge. You need a potential difference. And in particular, you need a complete path for electrons to flow, because if there's not a complete path, the electrons don't see a potential difference. For example, I'm going to build a very short circuit. So here's my light bulb. You got to remember this terminology. The symbols are in your reference table. Here's a resistor, and here's a switch, right? So this is a simple series circuit. A series circuit is one in which electrons can only take one path, right? And so this is where electrons go through the light bulb, go through the resistor, go through the switch when it's closed, and come back. So this is series circuit, it's one path. We know in a series circuit, and this is right off your reference table, the current is the same in each part. And the reason why it's the same is because electrons can't go faster than the electron in front of it. Remember the analogy I used in class. If you're in a one-lane street, you can't go faster than the car in front of it. You just can't, unless you want to crash into them, but electrons don't crash into each other like that. So that's why the current is all the same. Now, the potential difference is added up because it's kind of like you're running a hurdle race and you have a certain amount of energy, right? Once you run through the first hurdle, you have a little less energy. And then once you run through the second hurdle, the third hurdle, so on and so forth, you keep losing energy each time, but the energy loss equals the total energy. So when I close this switch, so right now this light bulb will not light because the switch is open. Because what ends up happening is I have a negative here and a positive here, right? And it can't connect because there's no connection, there's no potential difference, because there's nothing here to keep drawing the electrons. So once I close this switch, I make a complete path from positive to negative, and electrons can flow. And in this circuit, the total resistance or resistance equivalent, which is also called total resistance, is also like voltage. It's just added up over each part. So that in a nutshell is series circuit. This is also why we measure current in series. Current, when you have an ammeter, so remember that is an ammeter, circle with an A, is put in with the circuit because since the current is the same in all parts of the circuit, we don't want to change the current by measuring it. So we put a current in, or an ammeter in series. And the question that I asked in class is the resistance high or is the resistance low? And the resistance has to be really, really, really low because you want the electrons to flow right through it without changing the current. So an ammeter has a really low resistance. And yes, you need to know that because they will ask you questions on it. It's just good to know anyways. Okay, I'm almost done. We have a parallel circuit and a voltmeter, and then we're done. So now I'm going to make another battery, but this time we're going to make a parallel circuit. Remember, a parallel circuit is a circuit, and my board's going slow, is a circuit in which electrons can take multiple paths, right? So it's where electrons can take multiple paths. Now, remember, these notes are just the information. You should definitely go on to Castle Learning and you should practice some problems because remember, Regents problems are about the application of the notes. They're not just, oh, if I look at these video, I'll know how to do all the problems because that's not how it works. These are the application of the notes is what the Regents problems are. So you have to know this information, but you still have to do all the math and answer all the questions properly. So electrons can take multiple paths, right? So they split here at this resistor and then keep going this way. And the voltage, the total voltage is the same in a parallel circuit because it's like all the parts are connected directly to the battery. So they all get the same voltage. If one part of the circuit breaks, the other still works because there's still a complete path. Like, so for example, if I had broken the circuit right here, then this part will stop working. However, this will continue to work because the electrons can still go on the outside of the path and they can't go on the inside until I close the circuit. They'll both be the same brightness because they get the same voltage. Now, that's also why we hook a voltmeter in parallel because it doesn't change the voltage if we hook it in parallel. Also, a voltmeter resistance, the resistance on a voltmeter is really high. Because think about it. Electrons are like students. One second, really high. Electrons are like students. You like to take the path of least resistance. However, there are some students who take the hard path so that they can do well, so that they can get that A or they can get that A plus. And so even though the resistance is really high, electrons still go through that path because they will. There's a complete path there, and it's like that student who works really, really hard to get that A. So that is your circuits and electricity in a nutshell. Once again, please go to Castle Learning and practice problems because once again, these are just the notes, which the Regents problems require you to apply the notes.